today is mainly about phase diagrams. So let's make sure we have some definitions, solid, liquid, and gas. Hopefully most of these are pretty familiar. The new ones that we're going to talk a lot about today is how they change from a solid, liquid, and a gas. And so you've heard of that called states of matters, but from now on we are going to be using phases of matter to mean the same thing. So this is a solid phase, which is pretty low energy. They just vibrate in place. Okay, and then we have the liquid phase where they kind of flow around. Okay, a little bit more energy. And the gas phase, these molecules are all apart and they're kind of crazy and they have a lot of energy. They're bouncing around doing all sorts of crazy things. So there's a little bit of a comparison. Just don't call it a solid type of matter. A type of matter is if it's an element or a compound or a solution, a mixture. Solid phase, liquid phase, gas phase. So read super carefully. There's a lot of words that seem like they're similar, but in chemistry, they are not. So never make assumptions that way. So in stoichiometry, we're using 22.4 liters equals 1 mole at STP for gases. And you probably at this point don't even remember that STP is standard temperature and pressure. So this is just a little reminder that that volume for the number of moles is only at a very specific set of conditions. Okay, 0 degrees C in 1 atmosphere, and only if it is a gas. And in fact, it has to be an ideal gas. But right now, we're just kind of lumping a lot of stuff in there together. So we're reviewing to make sure 1 mole of carbon dioxide at STP is 22.4 liters. 1 mole of oxygen gas at STP is 22.4 liters. 1 mole of chlorine gas at STP is 22.4 liters because we are at the same temperature and pressure. So it is going to fill up the same amount of space. Okay, now you do not need to know normal temperature and pressure, but I want just to point it out that this molar volume that we're using for 22.4, there's a number for every standard or every temperature and pressure. So you could look on a chart and say, okay, what if I'm at 20 degrees C in 1 atmosphere? Then I have 24.05 liters is equal to 1 mole of gases at that pressure and temperature. So there is a specific number you can look at for every pressure and temperature, or you can use some equations, which we're going to be learning about later. Okay, but 1 mole of gases, if it's an ideal gas at the same temperature and pressure, it's going to have the same volume. So if it has the same number of moles and it's at the same temperature and pressure, it's going to have the same volume. Okay. What about its energy levels? When we're solid, remember at the beginning, vibrates in place, okay? Not a lot of energy, so not a lot of temperature, because temperature is the measure of how much is moving. The solid is just vibrating in place, where those gas was crazy, all over the place, bouncing around. So we have more temperature in gases. If I put some water on the stove to boil, I'm adding heat into that because it needs to get more energy so that it can bounce around. If I'm adding heat, I'm taking heat inside, so that is endothermic. So anytime you go from a solid to a liquid to a gas, or a solid to gas, it's endothermic. I had to take heat inside to make that change happen. So the other direction has to be exothermic. I had to take heat away. So it doesn't matter if we're talking about water and ice, or we're talking about a metal. Go back and think about that water on the stove. I have to add heat to go from a liquid to gas. So that's endothermic. So anytime I'm going to the right on the scale, endothermic. Anytime I'm going to the left, exothermic, every single time. Exo, the heat had to exit because that solid got cold and started moving slowly, started getting goosebumps. So it's just vibrating in place, but doesn't have a lot of energy. Okay, so because all the heat left. So we have a phase diagram, and that's going to help us determine the phase of a substance, because as we talked about before, that pressure and temperature is really indicative of how much volume something has, but it also tells us what state of matter. When you get these, they don't always have solid, liquid, and gas written. The one in the upper left is always your solid, and then you just go around clockwise. My next division is liquid, and my next one is gas. On some of the drawings, you are going to see a division over here on this side after the critical point, okay, where we're talking about the supercritical fluids. It's not on all of these because that is not what we are using in year one. We'll get into those more in year two. Okay. What else is on this phase diagram? When I go from a solid to a liquid, so if I had any point over here in the solid area, and then I increase the temperature because that temperature is low to high, and I'm just putting in numbers, it's not going to be 100 actually. But anytime I'm increasing the temperature, I'm going this way on the graph. So I'm going to go from the solid to the liquid region if my first point was here and my second point was there. When something goes from a solid to a liquid, what does it do? It melts. So you're going to be able to use a lot of the terminology you have already known before. How about if I get a point here and I make it colder? Then I'm going to the left and I'm crossing this solid liquid boundary line, and I'm going from the liquid to the solid, so I am freezing. If I have a point over here and my second point plots here, that's not a straight across, but that is still going across the liquid gas boundary line, the line that separates the liquid and the gas phase. So when we go from a liquid to a gas, that is vaporization, because we turned into a vapor. How about if I go the other direction? Okay, in this case, I just increased the pressure because I went up on the pressure scale. Increased the pressure in this case, took a point from it being in a gas phase to a liquid phase, from a gas to a liquid. When you have a soda and you leave it out on the counter, it starts sweating. That is condensation. So it doesn't matter that this arrow is not always going to be perfectly matched, but if the arrow goes from the gas to the liquid side, no matter what direction it's going, as long as it's going from the gas to the liquid, it's condensation. And the last two down here are at that boundary line. This boundary line is what? The solid gas boundary line. So if I'm going from a solid to a gas, that's called sublimation. It skipped the liquid stage. I go from a gas to a solid, it's the deposition phase. Now, if you plot a point from here to here, this is not sublimation. It didn't go from a solid to a gas. It went from a solid to a liquid to a gas. So again, be very, very specific when you're plotting your points and drawing things out. So let's go in and make sure we have all sorts of data information. This point here is the triple point. It's when the substance is a solid, liquid, and gas. It's on all three boundary lines. Where does water exist as a solid and a liquid? So if this graph was for water, where it would exist as a solid and a liquid is all along this line, because that is the line where it's converting from a solid to a liquid. So you can look at that for each one. Where does it occur, a solid and a gas at the same time? Down here. Where does it occur, all three? The triple point, solid, liquid, and gas. Critical point. Critical point is way here, and that means everything past it is critical or acts like a supercritical fluid. Okay, so the temperature is increasing, the pressure is increasing, and after that point, the liquid and gas properties become identical. normal boiling point, the boiling point at normal or standard pressure. So these are a good list of numbers to memorize, not just for remembering that they are all standard pressures, but they're also your conversion. 1 atmosphere is equal to 760 torrs. 1 atmosphere is also equal to 101,300 pascals. These are all equivalent things for standard pressure. They're just in different units. So this graph right here is kilopascals. So I need that 101.3. So they have a 101 here. So I'm just going to use that as my standard pressure line because it's pretty close for what we're working with. So if they want to know the boiling point at standard pressure, I'm going to draw a line at standard pressure, and then I got to find my boiling point. Where is my boiling point? My boiling point is when something changes from a liquid to a gas, or it boils. Which boundary line? The liquid gas boundary line. This is my liquid gas boundary line. And lo and behold, there is an intersection from the pressure, the standard pressure, and where it boils. So it can boil anywhere along this line, but I need the normal boiling point. So I need the boiling point on the standard pressure line, and that intersection is at 100 degrees, kind of giving me the idea that on this graph, we're talking about water. And they were nice enough on this one to label ice, solid, water, liquid, water, vapor, gas. So that's like, whew, when you're taking that SOL, oh yes, I know water boils at 100 degrees normally. So this was just confirmation. Always have physical proof. Don't assume. It just makes you feel good when you're like, okay, I did get the same answer they did. So describe the changes along the standard pressure line. Where's standard pressure? We're in kilopascals. It's at 101 degrees again. Go very slowly when you're describing these. So when we're describing, we're always going to go left to right. So we're going to start our explanation here. Okay, that's at not even 0 degrees. That's some sort of negative degrees C. Okay, so it's super cold and it is a solid, and it's going to continue on as a solid. This whole process, it is still a solid in here. Okay, and then it's just being heated. We're adding heat. So the kinetic energy or the movement energy of the molecules is increasing, but it's not enough for it to change phases yet until we get to this boundary line. Where is that boundary line? At 0 degrees. So at 0 degrees, the solid is phase changing to a liquid, and that is called melting. Okay. So solid to liquid, but then you need the definition, it's melting. Then we continue on all through here. We're a liquid, we're a liquid, we're a liquid, but we're increasing our kinetic energy. We're getting more erratic. We're getting more erratic. We hit the liquid gas boundary line and we boil. So at 100 degrees, we are boiling because we're changing from a liquid to a gas. And then we keep going on, gas, gas. This whole time here, we are just sticking in a gas country for that rest of the time. As we increase the temperature, our kinetic energy increases, our molecules are moving faster and more randomly, but we are staying in that water vapor area. How about this one? What happens when a substance goes from 100 degrees C at 0.6 kilopascals to twice standard pressure? So first I'm going to double check. All right, kilopascals, kilopascals. I don't need to do any conversion. Degrees C, degrees C. I don't need to do any conversion. I can just plot that point 100 degrees C and 0.6 kilopascals, and I'm going to find that intersection point on the graph. Okay, so it was the same as if I just drew a line over and drew a line up. That intersecting point is 0.1, 100 degrees C, 0.6 kilopascals. What is it right now? Right now, it is a gas. And then it's going to go to, so I have a second point to do at twice standard pressure. So I got to remember, okay, 101.3 is standard pressure. So 2 times standard pressure, 202.6. Wow, and I'm looking up here, I got 101 and 22,000, so I'm gonna have to estimate. Okay, so it's gonna be a lot closer to 101 than it is to 22,000. So I'm gonna estimate that it's somewhere here. It didn't give me a new temperature. What happens when the substance goes from 100 degrees C at 0.6 kilopascals to twice standard pressure? It does not give me another temperature. So you assume temperature is constant or unchanging. So my next point is going to be at 100 degrees C and at twice standard pressure. So my second point is going to be somewhere about there. And when I calculate with the ruler, I actually get it slightly higher, but you notice the same result is going to be the same. It is now in the liquid area. So if something goes from a gas to a liquid, it condenses. So what happened to the substance? At about, what point was the boundary? At standard pressure, it changed from a gas to a liquid and went through the condensation phase change. Okay, so lots of little words to write in there so that you're clear when you're picking the best choice on those problems. And that is all.